The dream of reaching another star system has captivated humanity for generations, and no destination seems more tantalizing than Proxima b, the closest known exoplanet orbiting within the habitable zone of Proxima Centauri, our nearest stellar neighbor. At just over 4 light-years away, it seems almost within reach compared to the vast cosmic distances that separate us from other potentially habitable worlds. Yet despite this relative proximity in astronomical terms, the reality of actually sending humans or even robotic probes to this alien world reveals a cascade of challenges so profound, so fundamentally rooted in the laws of physics and the limitations of our technology, that the journey remains firmly in the realm of science fiction for the foreseeable future. Understanding why Proxima b is effectively unreachable requires us to confront uncomfortable truths about our place in the universe, the nature of interstellar space, and the technological gulf between our current capabilities and what would be required to bridge even the smallest gaps between the stars. When we first consider the distance to Proxima b, our minds struggle to comprehend the sheer scale involved. 4.2 light-years sounds manageable when expressed in such simple terms, but translating this into units we can actually grasp reveals the true enormity of the challenge. This distance equals approximately 25 trillion miles or 40 trillion kilometers. To put this in perspective, if we were to travel at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reached speeds of approximately 430,000 miles per hour during its close approaches to the Sun, it would still take us nearly 7,000 years to reach Proxima b. That's longer than the entire span of recorded human civilization. We would need to maintain that incredible velocity continuously for a period stretching from before the construction of the pyramids in Egypt until today, and we still wouldn't have arrived. The Voyager 1 spacecraft, which has been traveling through space since 1977 and is now the most distant human-made object from Earth, moving at roughly 38,000 miles per hour, would require more than 70,000 years to cover the distance to Proxima Centauri if it were headed in that direction, which it isn't. The speed of light itself, the cosmic speed limit according to our current understanding of physics, presents the first fundamental barrier to any interstellar journey. Light travels at approximately 186,000 miles per second, and yet even at this breathtaking velocity, photons take 4.2 years to make the journey from Proxima Centauri to Earth. This means that the light we see from Proxima Centauri tonight actually left the star during early 2021. This temporal displacement is built into the very fabric of the universe, and it means that even if we could somehow achieve light-speed travel, which we'll explore the impossibility of shortly, we would still face a multi-year journey with no possibility of real-time communication with Earth. Any message we sent home would take 4.2 years to arrive, and any response would take another 4.2 years to reach us, creating an 8+ year communication lag that would make any kind of mission support or coordination extraordinarily difficult. But the speed of light isn't just a practical limitation. It's a theoretical maximum that, according to Einstein's special theory of relativity, cannot be reached by any object with mass. As an object with mass accelerates closer and closer to the speed of light, its relativistic mass increases, requiring ever more energy to continue accelerating. To actually reach the speed of light would require infinite energy, which is obviously impossible. This isn't just a technological hurdle we might overcome with better engineering. It's a fundamental law of the universe as we understand it. Even if we could somehow harness the entire energy output of our Sun for propulsion, we still couldn't accelerate a spacecraft with any significant mass to light speed. The mathematics of relativity are unforgiving in this regard, creating an asymptotic relationship where each incremental increase in velocity requires exponentially more energy as you approach the speed of light. The energy requirements for interstellar travel, even at far more modest velocities than light speed, are staggering beyond comprehension. Let's consider what it would take to send even a small probe to Proxima b at a reasonable fraction of light speed, say 10%, which would reduce the journey time to roughly 42 years. This might seem like a potentially achievable timeframe within a human lifespan, or at least within the operational lifetime of a well-designed spacecraft. However, accelerating even a tiny 1-gram probe to 10% of light speed would require approximately 450 trillion joules of energy, equivalent to the explosive yield of over 100 kilotons of TNT, roughly 5 times the energy released by the atomic bomb dropped on Nagasaki. This is the energy needed to accelerate a single gram, about the weight of a paperclip, to this velocity. A realistically sized probe, weighing even just a few hundred kilograms, would require proportionally more energy, quickly reaching levels that dwarf our entire global energy production. The total annual energy consumption of human civilization is approximately 600 exajoules, and we would need to dedicate a substantial fraction of this just to launch a single small probe on a one-way journey to our nearest neighbor star. The problem compounds when we consider that we don't just need to accelerate the spacecraft, we also need some method of slowing it down when it arrives. Otherwise, it will simply streak through the Proxima Centauri system at tremendous velocity, with only hours or perhaps days to conduct observations before leaving the system forever and hurtling off into the void beyond. Deceleration requires nearly as much energy as acceleration, which means we need to double our energy budget or carry fuel for braking, which exponentially increases the mass we need to accelerate in the first place. This is the tyranny of the rocket equation, first formulated by Konstantin Tsiolkovsky in the late 19th century, which demonstrates that the mass of fuel required increases exponentially with the desired change in velocity. For interstellar journeys, the fuel requirements quickly become absurd, requiring fuel masses many times greater than the payload mass, which in turn requires more fuel to accelerate that fuel, creating a vicious cycle that makes conventional rocket propulsion completely impractical for interstellar travel. Current rocket technology, which relies on chemical propulsion, is laughably inadequate for interstellar journeys. Chemical rockets achieve exhaust velocities of at most around 4.5 kilometers per second, which is effective for reaching Earth orbit or traveling within our solar system, but represents a tiny fraction of the velocity needed for interstellar travel. Even our most advanced ion drives and plasma engines, which achieve much higher exhaust velocities by electrically accelerating ions rather than relying on chemical combustion, still fall far short of what would be required. The Dawn spacecraft, which used ion propulsion to visit the asteroids Vesta and Ceres, achieved a total velocity change of about 11 kilometers per second over its mission lifetime. Impressive for deep space operations within our solar system, but representing less than 0.004% of the speed of light. Scaling up these technologies to achieve relativistic velocities isn't just a matter of engineering refinement. It would require fundamental breakthroughs in propulsion physics. Nuclear propulsion offers somewhat better prospects than chemical or electric propulsion, but still falls dramatically short of what interstellar travel demands. Nuclear fission engines, which use the heat from nuclear reactions to accelerate propellant, could theoretically achieve exhaust velocities several times higher than chemical rockets. Project Orion, conceived in the 1950s, proposed using a series of nuclear explosions behind a spacecraft to propel it forward, with each detonation providing a pulse of thrust absorbed by a massive pusher plate. Calculations suggested this approach might achieve velocities of up to 5% of light speed, which would reduce the journey to Proxima b to roughly 85 years. However, Project Orion faced insurmountable obstacles, including international treaties banning nuclear weapons in space, the engineering challenges of building a pusher plate that could withstand repeated nuclear blasts, and the moral and environmental concerns about detonating thousands of nuclear devices. The project was ultimately shelved, though its core concepts remain theoretically sound and continue to inspire modern propulsion research. Nuclear fusion offers even greater potential than fission, as fusion reactions release more energy per unit mass of fuel and could theoretically achieve exhaust velocities approaching a few percent of light speed. Various fusion propulsion concepts have been proposed, including magnetic confinement fusion drives and inertial confinement fusion designs. But all face the fundamental challenge that we haven't yet achieved: sustained, controlled fusion reactions that produce more energy than they consume, even in stationary terrestrial reactors. Extending fusion technology to a spacecraft environment where mass and volume constraints are extreme and where the reactor must operate reliably for decades without maintenance represents challenges many orders of magnitude greater than achieving fusion in ground-based facilities. Recent progress in fusion research, including the achievement of fusion ignition at the National Ignition Facility, offers hope that practical fusion energy may eventually be possible, but adapting these approaches to spacecraft propulsion remains a distant prospect. The most theoretically promising propulsion concept for interstellar travel is the antimatter rocket, which would harness the complete conversion of matter to energy according to Einstein's famous equation E equals mc squared. When matter and antimatter meet, they annihilate each other completely, releasing energy with perfect efficiency. A single kilogram of antimatter reacting with a kilogram of normal matter would release approximately 1.8 times 10 to the 17th joules of energy, equivalent to roughly 43 megatons of TNT. This energy density is unmatched by any other known energy source, making antimatter theoretically capable of propelling spacecraft to significant fractions of light speed. However, antimatter propulsion faces seemingly insurmountable practical obstacles. First, antimatter doesn't exist naturally in any significant quantities in our region of the universe, so we must manufacture it using particle accelerators. Current production rates are measured in nanograms per year at facilities like CERN, and the process is extraordinarily inefficient, consuming vastly more energy than the resulting antimatter contains. Producing even a single gram of antimatter, let alone the kilograms that would be needed for an interstellar mission, would require global industrial capacity dedicated solely to antimatter production for decades or centuries. Second, storing antimatter is incredibly difficult because the moment it comes into contact with normal matter, it annihilates, releasing its energy. Antimatter must be stored in magnetic or electric traps that prevent any contact with the container walls, and maintaining these traps requires constant energy input and perfect reliability over the decades-long duration of an interstellar journey. Any failure of the containment system would result in immediate catastrophic annihilation of the entire antimatter fuel supply. Even if we could solve the propulsion problem and accelerate a spacecraft to a significant fraction of light speed, the journey through interstellar space would be long and arduous. Space presents hazards that are difficult to overstate. Interstellar space is not empty vacuum, as is often imagined, but contains a thin but not insignificant density of gas and dust. The interstellar medium has an average density of approximately 1 atom per cubic centimeter, which seems negligibly sparse, but at relativistic velocities, even individual atoms become dangerous projectiles. At 10% of light speed, a hydrogen atom carries kinetic energy comparable to a rifle bullet. A spacecraft traveling at this velocity would experience constant bombardment from these high-energy particles, which would gradually erode any exposed surfaces and could penetrate deep into the spacecraft structure, damaging electronics, degrading materials, and potentially exposing any crew or sensitive instruments to harmful radiation. The spacecraft would need extensive shielding to protect against this erosion, But shielding adds mass, which increases the energy requirements for acceleration, creating yet another vicious cycle. At higher velocities approaching significant fractions of light speed, even individual atoms would strike with enough energy to trigger nuclear reactions, creating cascades of secondary radiation and potentially making the spacecraft itself radioactive over time. Interstellar space also contains dust grains, ranging from microscopic particles to larger chunks of rock and ice, any of which could catastrophically damage a spacecraft traveling at relativistic velocity. A collision with even a grain of sand at 10% of light speed would release kinetic energy equivalent to several kilograms of TNT, more than enough to vaporize a significant portion of the spacecraft. Detecting and avoiding these hazards would be extraordinarily difficult because at such high velocities, the spacecraft would have only fractions of a second to react once a particle was detected in its path. The spacecraft's sensors themselves would be limited by the speed of light, meaning that light reflected from an object ahead wouldn't reach the sensors until the object was extremely close, possibly too close to avoid. Some proposals suggest using magnetic fields to deflect charged particles or deploying sacrificial shielding ahead of the main spacecraft to absorb impacts. But these approaches add complexity and mass, while providing only partial protection. The reality is that any interstellar journey at relativistic velocities would be a hazardous passage through a cosmic shooting gallery, with the cumulative risk of catastrophic impact increasing with both journey distance and velocity. The cosmic radiation environment presents another severe challenge for interstellar travel, particularly for any mission carrying living organisms. Beyond Earth's protective magnetosphere and atmosphere, space is flooded with high-energy particles from various sources, including the solar wind, cosmic rays from distant supernova and other energetic events, and galactic cosmic radiation that pervades the entire galaxy. This radiation consists primarily of protons and heavier atomic nuclei, accelerated to nearly the speed of light, carrying enormous kinetic energies. When these particles strike matter, including biological tissue or electronic components, they deposit their energy in ways that can sever molecular bonds, damage DNA, destroy microelectronics, and degrade structural materials. Astronauts on the International Space Station, despite being only a few hundred miles above Earth's surface, still receive radiation doses roughly 100 times higher than people on Earth's surface, protected by the station's aluminum hull and partial shielding from Earth's magnetosphere. On an interstellar journey, radiation exposure would be even more severe and unrelenting, accumulating over the decades or centuries required to reach another star system. For human passengers, the radiation exposure during an interstellar journey would almost certainly be fatal without extraordinary shielding. Current estimates suggest that astronauts on a Mars mission would receive radiation doses approaching or exceeding safe lifetime limits, and Mars is a journey of just months within our own solar system, where the Sun's magnetosphere provides some protection from galactic cosmic rays. An interstellar journey would last orders of magnitude longer and would pass beyond all solar protection, exposing crew to the full intensity of galactic radiation for decades. The biological effects of such chronic radiation exposure are difficult to predict precisely because we've never exposed any living organism to such conditions, but they would certainly include dramatically increased cancer risk, damage to the central nervous system, cataracts, cardiovascular disease, and potential impacts on fertility and genetic integrity. Adequate shielding against cosmic rays requires substantial mass, because high-energy particles can penetrate most materials. The most effective shielding uses hydrogen-rich materials like water or polyethylene, which are better at absorbing particle energy than denser materials like lead. But protecting human passengers would still require shielding masses measured in tons per person, again driving up the total spacecraft mass and energy requirements to prohibitive levels. Even robotic missions face severe radiation challenges, though these are somewhat less constraining than for human missions. High-energy particles can cause single-event upsets in computer memory and processors, flipping bits and potentially causing software crashes or permanent hardware damage. Cumulative radiation exposure gradually degrades semiconductor materials, increasing electrical resistance and eventually causing complete failure of electronic components. Space-qualified electronics are designed to be more radiation-tolerant than commercial components, using techniques like radiation-hardened chip designs, redundant systems, and error-correcting codes. But even the most robust electronics have limits to the total radiation dose they can withstand. The electronics aboard an interstellar probe would need to survive decades of unrelenting cosmic ray bombardment, while maintaining the ability to navigate, collect data, communicate with Earth, and execute their mission. This requires not just radiation-hardened designs, but also substantial redundancy and self-repair capabilities, all of which add mass and complexity to an already challenging mission architecture. The communications challenges for an interstellar mission are profound and multifaceted. At Proxima Centauri's distance, even light-speed radio signals take 4.2 years to travel each direction, meaning any command sent from Earth would take 4.2 years to reach the spacecraft, and confirmation of that command's receipt would take another 4.2 years to return, creating a minimum 8.4-year round-trip communication time. This makes real-time control impossible and requires the spacecraft to operate with extraordinary autonomy, capable of detecting and responding to problems, making navigation corrections, and conducting its scientific mission entirely on its own, with no possibility of guidance from mission control. Every decision tree, every possible failure mode, every scientific protocol would need to be anticipated and programmed before launch, because by the time any unexpected situation could be communicated to Earth and a response received, the critical moment would have passed years ago. The power requirements for communication across interstellar distances are staggering. Radio signals obey the inverse square law, meaning their intensity decreases with the square of distance from the transmitter. At Proxima Centauri's distance, a radio signal would be spread over an area roughly 20 trillion times larger than at a distance of 1 astronomical unit, the Earth-Sun distance. To achieve the same received signal strength at Earth, the transmitter would need to be 20 trillion times more powerful, or the receiving antenna would need to be 20 trillion times more sensitive, or some combination thereof. Even with the largest conceivable radio telescopes on Earth and the most efficient transmitters on the spacecraft, data transmission rates would be painfully slow, likely measured in bits per second rather than the megabits or gigabits per second we've become accustomed to for communications within our solar system. Transmitting even a single high-resolution image might take days or weeks, and the total data return from the mission would be severely limited by these communication constraints. The spacecraft would need to be extraordinarily selective about what data to transmit, potentially discarding 99% or more of what it collects and sending only the most scientifically valuable information. Power generation for an interstellar spacecraft presents its own unique challenges. Within our solar system, many spacecraft use solar panels to generate electricity, taking advantage of the abundant sunlight available. However, solar intensity decreases with the square of distance from the Sun, and beyond the orbit of Mars, solar panels become progressively less practical. At Proxima Centauri's distance, solar intensity from our Sun would be utterly negligible, making solar power completely useless for the interstellar transit portion of the journey. The spacecraft would need to carry its own power source, capable of operating reliably for decades without maintenance. Radioisotope thermoelectric generators, or RTGs, which convert heat from radioactive decay into electricity, have powered many deep space missions, including the Voyager probes and the Curiosity and Perseverance Mars rovers. However, RTGs have limited power output, and their radioactive fuel has a half-life that limits their operational lifetime. Plutonium-238, the most commonly used fuel, has a half-life of 88 years, meaning its power output decreases noticeably over the decades required for an interstellar journey. More significantly, RTGs are heavy and produce relatively little power, typically measured in hundreds of watts. An interstellar spacecraft would need significantly more power to operate its systems, communicate with Earth, and potentially run science instruments at the destination, requiring multiple RTGs or a different power source entirely. Nuclear fission reactors offer higher power output than RTGs and could theoretically operate for decades, but they add substantial mass and complexity. A fission reactor requires not just the nuclear fuel, but also a moderator to control the reaction, shielding to protect other spacecraft systems from radiation, heat exchangers to extract the thermal energy and convert it to electricity, and all the control systems needed to maintain safe operation. The reactor would need to operate flawlessly for the entire mission duration, because any malfunction could disable the spacecraft, and repair would be impossible. The Soviet Union flew a series of nuclear reactor-powered satellites called the RORSAT program, and the United States developed the SNAP-10A reactor that operated in space for 43 days before a non-nuclear component failure shut it down. These experiences demonstrated both the feasibility and the challenges of space nuclear power. But scaling this technology to the power levels and lifetimes required for interstellar missions remains an unsolved engineering problem. Alternative power sources, like fusion reactors or antimatter annihilation, could theoretically provide more power with less mass. But these technologies face all the previously mentioned challenges of being far beyond our current capabilities. Navigation across interstellar distances requires extraordinary precision that challenges our current capabilities. Within our solar system, we navigate using a combination of ground-based tracking of radio signals, onboard inertial measurement units, and optical observations of known objects like planets, moons, and stars. For an interstellar mission, ground-based tracking becomes progressively less useful as the spacecraft recedes to enormous distances where even slight uncertainties in measurement translate to huge positional errors. The spacecraft would need to navigate primarily autonomously, using star sightings to determine its orientation and possibly pulsars, which emit regular pulses of radio energy as cosmic navigation beacons. However, even with perfect knowledge of position and velocity, plotting a course to Proxima b is complicated by the fact that stars themselves are in motion, following their orbits around the galactic center. Proxima Centauri is moving relative to our solar system at approximately 22 kilometers per second, and over the decades required for an interstellar journey, both our solar system and Proxima will move significant distances through space. The spacecraft would need to aim not at where Proxima is now, but where it will be when the spacecraft arrives decades hence, requiring precise knowledge of Proxima's motion and precise control over the spacecraft's trajectory throughout the journey. The psychological and social challenges of human interstellar travel are profound and perhaps as daunting as the technical challenges. A journey to Proxima b would take at minimum several decades, even with optimistic propulsion assumptions, and more realistically would require centuries with any technology we can currently envision. No individual human could expect to survive the journey, meaning that any crewed mission would necessarily be a multi-generational ship, where the people who arrive at Proxima b would be the distant descendants of those who departed from Earth. The psychological implications of this scenario are difficult to fully grasp. The travelers would know that they would spend their entire lives confined within a spacecraft, never setting foot on Earth again, never breathing unrecycled air, never seeing open sky, never experiencing any environment that wasn't artificially created and maintained. Subsequent generations born aboard the ship would face an even stranger existence, knowing only the artificial environment of the spacecraft, with Earth itself becoming increasingly abstract and distant, known only through records and stories passed down from their ancestors. Maintaining social cohesion and purpose across multiple generations of space travelers would be extraordinarily challenging. The initial generation might be sustained by the excitement and purpose of being pioneers setting out on humanity's first interstellar journey. But how would their children and grandchildren find meaning in a mission they didn't choose? Traveling toward a destination they'll never see, living out their lives in cramped artificial habitats. The risk of social breakdown, conflict, loss of purpose, and potential rebellion against the mission would be substantial. Historical examples of isolated communities, from Antarctic research stations to remote island populations, demonstrate that even the best planned social structures can develop unexpected dysfunctions over time, and the unique pressures of an interstellar generation ship would be unprecedented in human history. The ship would need to maintain not just physical systems, but also cultural, educational, and social systems across the generations, preserving the knowledge and motivation required to complete the mission while allowing for the natural evolution and change that characterizes all human societies. The genetic and health challenges of a multi-generation space crew add yet another layer of complexity. The founding population would need to be large enough to avoid the genetic bottleneck, which causes harmful recessive traits to become more common and reduces overall genetic diversity. Population geneticists generally estimate that a founding population of at least a few hundred unrelated individuals would be necessary to maintain genetic health across multiple generations, though some estimates suggest several thousand might be needed for long-term viability. This population requirement directly multiplies all the mass, life support, food, water, and space requirements of the mission, making the spacecraft enormously larger and more complex than a simple probe or even a single-generation cruise ship. Each individual requires approximately 1 kilogram of food, water, and oxygen per day, meaning the life support requirements alone for a population of several hundred over a century-long journey would amount to thousands of tons of supplies unless the ship can achieve completely closed-loop recycling of all consumables, which remains technologically challenging even for shorter durations. The spacecraft would essentially need to be a completely self-sustaining ecosystem, recycling air, water, and waste with perfect efficiency, growing food continuously through hydroponics or other cultivation methods, and maintaining all systems indefinitely without external support. The International Space Station, our most advanced long-duration space habitat, can recycle much of its water and oxygen, but still requires regular resupply missions from Earth to replenish consumables, spare parts, and equipment. Extending these life support systems to operate with complete closure for decades or centuries without any external inputs represents an enormous leap in capability. Any failure in these systems would be immediately life-threatening, and the redundancy and reliability requirements would be extreme. The spacecraft would need manufacturing capabilities to produce spare parts and repair components as things inevitably break down, requiring not just storage of raw materials, but also machine shops, electronics fabrication facilities, and the knowledge and skills to maintain and repair every system aboard the ship across multiple generations. Medical care for a multi-generation crew presents unique challenges that we've barely begun to address. The crew would need complete medical facilities capable of handling everything from routine care to emergency surgery, childbirth, and long-term treatment of chronic conditions, all without the possibility of evacuation to Earth or consultation with specialists beyond the 8-plus-year communication delay. The ship would need to carry a complete pharmacy of medications. But most drugs have limited shelf lives and would degrade over the decades of the journey, requiring either massive stockpiles to account for degradation or the capability to synthesize medications aboard the ship from raw chemical precursors. Genetic counseling would be essential to minimize the risk of hereditary diseases in an isolated population where the gene pool is limited. The crew would need doctors, surgeons, dentists, and other medical specialists, but also the ability to train new medical professionals from among the population born during the journey, requiring comprehensive educational facilities and programs to transmit knowledge across generations. The philosophical and ethical questions surrounding interstellar colonization are profound and perhaps unresolvable. Do we have the right to commit unborn generations to a life of confinement and hardship they never chose? How do we ensure that the mission can be ethically terminated if circumstances change or problems arise, when turning back or stopping would doom everyone aboard? What governance structures should manage the ship, and how do we prevent the development of authoritarian control or social stratification in an environment where there's no possibility of leaving or external oversight? If we eventually reach Proxima b and find that it harbors life, even microbial life, do we have the right to establish a human presence that might contaminate or disrupt that ecosystem? These questions have no easy answers, and different people with different values would answer them differently, yet any actual interstellar mission would need to grapple with them in concrete terms. The economics of interstellar travel present another seemingly insurmountable barrier. Even the most optimistic cost estimates for an interstellar mission run into the trillions of dollars or equivalent resources, representing a significant fraction of global GDP, sustained over decades of mission development and construction. For comparison, the Apollo program that put humans on the moon, often cited as an example of what humanity can achieve when we commit to a goal, cost approximately $25 billion in 1970s money, equivalent to roughly $250 billion in current dollars, and represented about 2.5% of the United States federal budget at its peak. An interstellar mission would be orders of magnitude more expensive and take orders of magnitude longer to complete, requiring sustained will and resource commitment across multiple generations of leadership and changing circumstances. The International Space Station, a far more modest endeavor than an interstellar mission, has cost over $150 billion over its construction and operational lifetime, and it orbits just a few hundred miles above Earth's surface, where it can be accessed and resupplied regularly. The return on investment for an interstellar mission is also fundamentally different from any previous space endeavor. The Apollo program returned samples from the moon within days, and astronauts came home to ticker tape parades within weeks of launching. An interstellar mission would require multiple human lifetimes before returning any data, and the people who funded and built the mission would never live to see its results. This creates a temporal disconnect between cost and benefit that challenges normal human decision-making. How do we justify spending trillions of dollars on a mission whose benefits won't be realized for centuries, when those same resources could address pressing problems in the present? This isn't to say such an investment couldn't be justified. The advancement of human knowledge and the long-term survival of our species are worthy goals. But it does illustrate the unique challenge of mobilizing resources for a project with such an extended time horizon. The technological readiness level of interstellar travel is also sobering when assessed honestly. NASA uses a scale called Technology Readiness Levels, or TRLs, to assess the maturity of technologies, ranging from TRL 1 for basic principles observed through TRL-9 for actual system proven in operational environment. Most of the technologies required for interstellar travel, from propulsion systems capable of reaching even small fractions of light speed to closed-loop life support systems capable of operating for decades, to autonomous navigation and decision-making systems sophisticated enough to handle any conceivable problem, are currently at TRL 1 or 2 at best. Many are purely theoretical concepts that haven't even been demonstrated in laboratory conditions, let alone in the space environment where they would need to operate. The gap between TRL-1 or 2 and TRL-9 typically takes decades to bridge, even for comparatively simple technologies, and the complex systems required for interstellar travel are among the most challenging engineering problems ever contemplated. Some have proposed alternative approaches that might make interstellar travel slightly more feasible, though each comes with its own severe limitations. The concept of a laser sail or light sail proposes using intense laser beams from Earth to accelerate an extremely lightweight spacecraft that uses a large reflective sail to capture the momentum of photons. By keeping the propulsion system on Earth or in Earth orbit, rather than carrying it aboard the spacecraft, this approach avoids the rocket equation's tyranny and could theoretically accelerate small probes to significant fractions of light speed. The Breakthrough Starshot initiative, funded by billionaire Yuri Milner and supported by prominent scientists, including the late Stephen Hawking, has proposed building an array of powerful lasers capable of accelerating gram-scale chip-sized spacecraft to 20% of light speed, which would reach Proxima Centauri in roughly 20 years, plus the 4.2 years for the signal to return to Earth. However, this approach faces enormous technical challenges, including the need for lasers with power outputs measured in gigawatts, focused with extraordinary precision on a small sail millions of kilometers away, keeping the sail from burning up under the intense laser light, and squeezing all necessary sensors, computers, and communication systems into a package weighing only a few grams. Even if these challenges could be overcome, the chip-sized spacecraft would have no capability to slow down upon arrival and would streak through the Proxima Centauri system at 20% of light speed, with only hours to make observations before departing forever into interstellar space. Another speculative approach involves waiting for technology to advance sufficiently that the journey becomes feasible, with later missions potentially overtaking earlier ones launched with inferior technology. This weight calculation, sometimes called the interstellar weight equation, suggests that if propulsion technology is improving fast enough, it might be better to delay launch until faster engines are available, even though this means a later launch, because the faster speeds might result in an earlier arrival. However, this logic quickly leads to paradoxical situations where we perpetually wait for better technology, never actually launching. Moreover, the assumption that propulsion technology will continue improving indefinitely may be overly optimistic, as we may be approaching fundamental physical limits rather than merely engineering constraints. Chemical rockets have improved relatively little in fundamental performance over the past 50 years. And while electric propulsion has advanced significantly, it still falls far short of what interstellar travel requires. Some futurists propose that we might not need to send physical spacecraft at all, instead transmitting information about human consciousness, genetic codes, or blueprints for human bodies to a destination where they could be reconstructed, either by previously sent equipment or by autonomous systems. This approach, sometimes called digital colonization or transmitted civilization, would allow information to travel at light speed while avoiding all the mass and energy constraints of physical travel. However, this concept raises profound philosophical questions about personal identity and continuity of consciousness. Is a reconstructed copy of a human the same person as the original, or merely a replica? Even if we could transmit and reconstruct a human body perfectly, which raises its own enormous technical challenges, we would be creating new individuals rather than actually transporting existing people across interstellar distances. For many people, this distinction would be philosophically and ethically significant, though others might consider it an acceptable compromise if it's the only feasible path to spreading human presence or consciousness to other stars. The possibility of discovering fundamentally new physics that circumvents current limitations remains, in principle, open. But betting on such discoveries as a solution to interstellar travel is speculative at best. Science fiction has imagined various faster-than-light propulsion methods, including warp drives that contract space in front of a spacecraft while expanding it behind, wormholes that create shortcuts through space-time, or hyperspace dimensions that allow shortcuts around normal space. While some of these concepts can be expressed mathematically within general relativity, they typically require exotic forms of matter or energy with properties never observed in nature, such as negative mass or negative energy density. The Alcubierre warp drive metric, proposed by physicist Miguel Alcubierre in 1994, is often cited as a possible path to faster-than-light travel consistent with general relativity, but it requires forms of exotic matter that may not exist and would need them in quantities that might equal the mass energy of entire planets or stars. More fundamentally, our current understanding of physics may be incomplete, and there could be phenomena or possibilities we haven't yet discovered, but constructing plans around hoped-for future discoveries in physics is not a reliable foundation for mission planning. The reality we must face is that with our current understanding of physics and engineering, and even with optimistic projections of technological advancement, interstellar travel to Proxima b remains beyond our capabilities for the foreseeable future, meaning decades and quite possibly centuries. This doesn't mean we should abandon interest in exoplanets or stop studying Proxima b and other potentially habitable worlds around other stars. Remote observation, using ever more sophisticated telescopes, can teach us much about these distant worlds, potentially revealing atmospheric compositions, surface conditions, and even biosignatures that might indicate the presence of life. The coming generation of extremely large telescopes, both ground-based and space-based, will give us unprecedented views of exoplanets, potentially allowing us to characterize their atmospheres in enough detail to assess their habitability or detect the presence of biologically produced gases like oxygen and methane in combinations that suggest active biospheres. What our limitations on interstellar travel really teach us is humility about our place in the universe and the vast scales involved in cosmic geography. The stars are genuinely distant in a way that goes beyond mere numbers, separated from us by gaps that may prove permanently unbridgeable for creatures of flesh and blood, with lifespans measured in decades. The universe is under no obligation to make itself conveniently accessible to us, and the fact that we can see stars and even detect planets around them doesn't imply that we can reach them with any technology we can currently imagine. The human tendency is to see technological progress as an inevitable march toward greater capabilities, assuming that any challenge is merely an engineering problem waiting to be solved with enough resources and ingenuity. Sometimes this optimism is justified, as when we split the atom, decoded the human genome, or built machines that can think. But sometimes the universe imposes limits that are not merely practical, but fundamental, rooted in the basic laws of physics that govern all matter and energy. This recognition needn't be discouraging or seen as a counsel of despair. Understanding our limitations can refocus our efforts on what is actually achievable, from building sustainable civilizations on Earth to expanding gradually and carefully throughout our own solar system to developing technologies for long-term human presence in space environments. Our solar system contains enormous resources and opportunities for exploration and expansion, from the potential subsurface oceans of moons like Europa and Enceladus that might harbor life, to the vast asteroid belt rich in metals and minerals, to the outer planets and their diverse moons that present environments unlike anything found on Earth. Learning to thrive in these environments, developing closed-loop life support systems, building sustainable habitats in space, and establishing permanent human presence beyond Earth would be achievements of historic significance, even if they don't satisfy our deepest longings to reach for other stars. The psychological impact of recognizing interstellar travel's near impossibility also deserves consideration, as it fundamentally shapes how we think about humanity's cosmic future and our relationship with the universe. For generations, science fiction has trained us to expect a future where humanity spreads across the galaxy, establishing colonies on countless worlds and encountering diverse alien civilizations. This vision has become so embedded in our cultural imagination that accepting the likely reality of permanent isolation within our solar system can feel like a loss, a limitation on human potential and destiny. Yet this recognition also carries a certain poignancy and beauty, suggesting that Earth and our solar system are not merely way stations on a journey to elsewhere, but rather our permanent home, deserving of our full attention and care. If we cannot easily escape to other star systems, then the preservation and flourishing of life on Earth and potentially throughout our solar system becomes not just important, but existentially critical. The question of alien life and the possibility of contact takes on different dimensions when we acknowledge the barriers to interstellar travel. If these barriers are truly fundamental rather than merely technological, then they apply not just to humanity, but to any civilization anywhere in the universe. This could partially explain the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing somewhere in our galaxy and the complete absence of any evidence for their existence or visits to Earth. If interstellar travel is effectively impossible for anyone, then even a galaxy teeming with intelligent life would consist of isolated civilizations, each confined to their own solar systems, unable to physically reach or visit each other, despite being aware through astronomical observations that other worlds and potentially other civilizations exist. Communication across interstellar distances through radio or optical signals would remain possible, though limited by the speed of light and the enormous time delays involved. But physical contact, trade, or cultural exchange would be impossible. Each civilization would develop in isolation, following its own unique trajectory, forever separated from all others by unbridgeable gulfs of space. This isolation might actually be beneficial in some ways, as it would prevent hostile civilizations from threatening each other and would preserve the diversity of independent evolutionary and cultural paths. Science fiction often portrays alien contact as either utopian cooperation or existential conflict, but if interstellar travel is impossible, both scenarios become moot. Civilizations could observe each other from afar, perhaps communicate across the decades or centuries of light-speed signal delay, but could never directly interfere with each other for good or ill. This enforced isolation could be seen as a kind of cosmic quarantine, ensuring that each world's biosphere and civilization develops according to its own internal logic, without external contamination or conquest. The universe might be filled with life and intelligence, yet each instance remains fundamentally alone, able to know of others, but never to reach them. The energetic and engineering requirements we've discussed also illuminate why we haven't been visited by aliens, assuming they exist. If traveling between stars is monumentally difficult for us, it would be monumentally difficult for them as well, regardless of how advanced they might be. While it's possible that some civilization somewhere has discovered physics unknown to us that enables easier interstellar travel, we have no evidence for such physics and cannot plan around speculative possibilities. The absence of alien visitors or obvious signs of alien technology in our solar system is consistent with a universe where interstellar travel is rare or non-existent, even if life and intelligence are common. The distances are simply too vast, the energy requirements too extreme, and the journey times too long for casual tourism or routine travel between stars. Any civilization undertaking such a journey would need compelling reasons to justify the enormous resource investment, and they would face all the same fundamental physical constraints that limit us. The concept of time itself becomes warped and strange when contemplating interstellar journeys. Einstein's theory of special relativity predicts that time passes more slowly for objects moving at relativistic speeds relative to stationary observers, an effect called time dilation. For a spacecraft traveling at 90% of light speed, time aboard the ship would pass at less than half the rate of time on Earth, meaning that subjectively for the travelers, the journey to Proxima b might take only 2 or 3 years, while more than 4 years pass on Earth. At 99% of light speed, time dilation becomes even more extreme, with the subjective journey time shrinking to mere months while years pass in the outside universe. At 99.9% of light speed, the journey might feel like only weeks to the travelers. This time dilation effect could potentially make interstellar travel psychologically bearable for crews, as they wouldn't need to endure decades of travel time subjectively, even though decades or longer would pass for everyone not on the ship. However, this apparent solution to the time problem creates its own profound challenges and paradoxes. The time dilation that makes the journey shorter for travelers also means they would be traveling into Earth's future, arriving back to find that everyone they knew had aged or died, that society had changed beyond recognition, and that they had become time travelers of a sort, disconnected from their original temporal context. Each journey would be a one-way trip, not just through space, but through time, severing connections with everything left behind. Moreover, achieving the velocities required for significant time dilation brings us back to the energy requirements we discussed earlier, which become ever more extreme as we approach light speed. The time dilation benefit only applies if we can actually achieve these velocities, and doing so requires solving all the propulsion, energy, and survival challenges that make interstellar travel so difficult in the first place. The scientific return from an interstellar mission, while potentially extraordinary, must also be weighed against the enormous costs and challenges. What could we learn from Proxima b that would justify the expenditure of a significant fraction of human civilization's resources over decades or centuries? The planet is approximately 1.1 to 1.5 times Earth's mass and orbits within Proxima Centauri's habitable zone, the region where liquid water could potentially exist on a planet's surface. However, Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun, which means Proxima b orbits very close to its star, completing an orbit every 11.2 days. This proximity subjects the planet to intense stellar flares and radiation, as red dwarf stars are notoriously active and temperamental, regularly unleashing powerful bursts of radiation and charged particles. These flares could strip away any atmosphere the planet might have and would create a harsh radiation environment on the surface, potentially making the planet uninhabitable despite being in the nominal habitable zone. Additionally, Proxima b is likely tidally locked to its star, meaning the same side always faces the star, just as the same side of the Moon always faces Earth. This would create extreme temperature differences between the day side and night side, with one hemisphere baked by constant starlight and the other frozen in perpetual darkness. Such conditions could make it very difficult for life to exist, though some models suggest that with a sufficient atmosphere to redistribute heat, the terminator zone between day and night sides might maintain habitable temperatures. We could learn much of this information through advanced telescopic observations from our solar system, using spectroscopy to analyze the planet's atmosphere if it has one, searching for biosignatures, and studying its surface conditions. While actually visiting the planet would certainly provide more detailed and comprehensive data, the marginal scientific benefit of a physical visit compared to remote observation might not justify the exponentially greater cost and risk. The question of what to do with the knowledge that interstellar travel is effectively impossible for the foreseeable future leads to different philosophical and practical responses. Some might advocate for aggressive investment in fundamental physics research in hopes of discovering new principles that could enable easier interstellar travel, though this approach risks spending enormous resources on what might prove impossible. Others might suggest focusing on robotic exploration within our solar system and increasingly sophisticated remote observation of exoplanets, maximizing our knowledge while accepting the limitation on physical travel. Still others might argue for multi-generational research programs aimed at incrementally improving propulsion technology, accepting that any actual interstellar mission would be a project for our distant descendants rather than our own generation. Each approach has merits and reflects different values regarding resource allocation, risk tolerance, and temporal perspective. One often overlooked aspect of the interstellar travel challenge is the problem of deceleration and orbit insertion upon arrival at the destination. Most discussions of interstellar propulsion focus on achieving high velocities, but any useful mission must also slow down enough to actually observe and study the destination system. A probe that streaks through at 20% of light speed would have only hours or days in the vicinity of Proxima Centauri before departing the system forever, hardly enough time to conduct meaningful observations. Slowing down requires either carrying additional fuel for braking, which exponentially increases the initial mass that must be accelerated, or using other deceleration methods such as a magnetic sail that drags against the interstellar medium, a brake sail that deploys to create drag, or potentially a laser or particle beam fired from the destination system to decelerate arriving spacecraft, which would require infrastructure to be established at the destination before the mission even launches. Each deceleration method presents unique challenges and limitations. Carrying fuel for braking essentially doubles the fuel budget, creating a cascade of increasing mass that quickly becomes impossible with any known propulsion method. A magnetic sail, which deploys a loop of superconducting wire to create a magnetic field that interacts with charged particles in space, could potentially provide drag for deceleration without requiring fuel, but it would only be effective at reducing velocity by small percentages, not bringing a relativistic spacecraft to a complete stop or even to orbital velocity. The drag would also extend over astronomical distances and require years or decades to slow the craft significantly. A brake sail, essentially a large deployable surface that creates drag against interstellar particles, faces similar limitations and would need to be enormous to provide meaningful deceleration. Using a laser beam from the destination to decelerate requires that infrastructure be already present there, creating a chicken and egg problem where the first mission to any star system would have no means of slowing down. The psychological and philosophical dimensions of attempting an interstellar mission extend beyond the immediate challenges facing any crew or the generations that follow them. There's something profoundly existential about setting out on a journey that will take longer than any individual human lifespan, knowing that you personally will never see the destination, that your children won't see it, and that perhaps your great-great-grandchildren might be the first to arrive at a world their ancestors left Earth to reach. This temporal displacement raises questions about personal identity and continuity of purpose across generations. In what sense is it the same mission when the people who arrive share only genetic descent and cultural transmission from those who departed? How do we maintain institutional memory and purpose across the decades or centuries of travel when everything else about human civilization, culture, and technology will have changed beyond recognition? Historical precedents for multi-generational projects are limited and not entirely encouraging. Medieval cathedrals sometimes took centuries to complete, with the original architects and builders never seeing the finished structure. Yet these projects maintained continuity of purpose because they remained connected to their surrounding societies, which provided resources, labor, and motivation across the generations. An interstellar generation ship would be isolated and autonomous, unable to draw on external support or motivation beyond what exists within the ship's community. The ship's society would need to maintain not just technical systems, but also cultural systems of meaning and purpose, robust enough to survive across generations in an artificial environment completely disconnected from Earth. Whether this is psychologically and socially sustainable remains an open and troubling question. The matter of crew selection for a multi-generational ship presents ethical and practical quandaries that amplify the mission's difficulty. The first generation would need to be volunteers who understand and accept the sacrifice they're making. But what about their children, who would be born into confinement without choice? Do parents have the right to make such a decision for children not yet born? How do we ensure genetic diversity in the founding population without coercion? What psychological profiles and skills should we select for, knowing that the descendants might have very different traits due to both genetic variation and the unique selective pressures of the spacecraft environment? The founding population would need to include not just astronauts and scientists, but also educators, doctors, farmers, engineers, craftspeople, artists, and all the diverse skills necessary to maintain a complete, if miniature, society. The number of people required multiplies with each role, and the spacecraft mass, life support burden, and complexity grow accordingly. Even with perfect planning, unexpected challenges would inevitably arise during an interstellar voyage lasting decades or centuries. Equipment would fail in unanticipated ways. Social tensions would develop that couldn't have been predicted. New diseases might emerge in the isolated population, and situations would arise requiring decisions and solutions that weren't programmed into the mission architecture before departure. The spacecraft would need not just redundancy and reliability in its technical systems, but also flexibility and adaptability in its social systems, the ability to respond to problems that couldn't have been anticipated, and develop new solutions using only the resources available aboard the ship. This requires a level of self-sufficiency and resilience that we've never achieved in any human system, as even the most isolated historical human communities could eventually receive outside help, or at least had the option of migration if conditions became unbearable. The question of governance on a generation ship deserves careful consideration, as the political structure chosen would shape the entire society that develops during the voyage. An authoritarian command structure might ensure mission continuity and prevent dangerous conflicts, but could lead to oppression and abuse, with no possibility of escape or outside intervention. A democratic system might better respect individual rights and allow for adaptation to changing circumstances, but could potentially lead to mission-threatening decisions if the population votes to abandon the mission or make changes that jeopardize its success. How do we balance the needs of the mission against the rights and autonomy of individuals who didn't choose to be part of it? What mechanisms prevent the emergence of hereditary aristocracies or other forms of rigid social stratification in an environment where there's no possibility of social mobility through migration? These are questions that philosophers and political theorists have grappled with for millennia in terrestrial contexts, and they become even more acute in the closed system of a generation ship. The possibility of mission failure looms over any interstellar endeavor, and the consequences would be catastrophic in a way that distinguishes interstellar missions from any previous human exploration. When previous exploration missions have failed, whether historical expeditions that never returned or space missions lost to accidents, the loss was tragic but limited in scope to the individuals directly involved and perhaps their immediate families and communities. An interstellar generation ship represents not just a crew but an entire micro-civilization, potentially thousands of people, including children born during the voyage. If such a mission fails through technical malfunction, ecological collapse of life support systems, social breakdown, or any of countless other possible catastrophes, we would lose not just individual explorers, but an entire community, and we would likely never know what happened to them. The distances and communication delays mean that by the time we realize something has gone wrong, the disaster would already be years or decades in the past, with no possibility of rescue or even of learning lessons that might prevent similar failures in future missions. The infrastructure required to support even a modest interstellar exploration program would be extraordinary, extending far beyond the spacecraft themselves. We would need extensive facilities in Earth orbit, or at locations like the Moon or asteroids, to construct the spacecraft, as their size and mass would make launching them directly from Earth's surface impractical or impossible. We would need energy generation and storage infrastructure on an unprecedented scale to charge propulsion systems or power laser arrays for beam-propelled craft. We would need global or at least international communications networks to maintain contact with spacecraft over interstellar distances. We would need educational and research institutions dedicated to maintaining the specialized knowledge required for interstellar missions across the decades or centuries of mission duration. This infrastructure would itself require enormous investment and international cooperation, and it would need to be maintained for timescales that exceed the lifetimes of any individual institution, or perhaps even any current nation-state. The international cooperation required for an interstellar mission may be one of its most significant challenges, possibly exceeding even the technical difficulties. Previous major space endeavors, like the International Space Station, have required cooperation between multiple nations, and this cooperation has proven fragile, subject to tensions and changing priorities. An interstellar mission would require sustained cooperation, not just for the years or decades needed to build the spacecraft, but for the entire duration of the mission, which might span centuries. Landscapes change, alliances shift, nations rise and fall, and yet the mission would require continuity of support across all these changes. How do we create institutional structures and international agreements robust enough to survive across such timescales? History provides few, if any, examples of international cooperation sustained for centuries, and most long-lived institutions have been cultural rather than scientific or technological in nature. The environmental impact of developing interstellar capability also deserves consideration, particularly the energy requirements we discussed earlier. Channeling a significant fraction of global energy production toward an interstellar mission could have profound effects on Earth's environment and society. The construction of the massive lasers needed for beam-propelled craft or the industrial capacity needed to manufacture antimatter would require resources and generate waste heat that could impact climate and ecosystems. Nuclear propulsion systems raise concerns about radioactive materials being launched from Earth, with the risk of accidents during launch potentially dispersing radioactive material across large areas. While these environmental concerns might be manageable with proper planning and safeguards, they add another layer of complexity and potential opposition to any interstellar program. The problem of contamination works in both directions and raises important ethical questions about interstellar exploration. Forward contamination refers to the risk that spacecraft from Earth might carry terrestrial microorganisms to other worlds, potentially contaminating pristine environments or competing with any native life forms. Despite our best sterilization efforts, spacecraft are never completely sterile, and hardy terrestrial microbes might survive the journey to another star and potentially colonize a new world. If Proxima b or any other destination harbors its own life, even microbial life, the introduction of terrestrial organisms could be catastrophic for that native ecosystem. Backward contamination, bringing alien organisms back to Earth, presents different risks that could potentially threaten terrestrial ecosystems if alien life proves compatible enough with Earth's biochemistry to reproduce here. While these risks might seem remote, given the difficulty of interstellar travel in the first place, they illustrate how even attempting such missions raises ethical questions we're not fully prepared to answer. The role of artificial intelligence in interstellar exploration deserves special attention, as it might prove to be the most practical approach to studying other star systems, even if physical human travel remains impossible. Autonomous robotic probes with sophisticated AI systems could potentially explore other worlds, make independent decisions about where to focus observations, and conduct scientific investigations without the need for life support, food, or the psychological accommodations required by humans. AI systems don't experience boredom or isolation during decades-long journeys, don't require gravity or breathable atmosphere, and can potentially be designed to repair themselves or even replicate using resources found at the destination. If we can develop sufficiently advanced AI before we develop the propulsion systems needed for interstellar travel, it might make more sense to send artificial intelligence as our representatives to the stars rather than risking human lives on such dangerous journeys. However, AI-based exploration raises its own philosophical questions about the meaning and value of exploration. Is there something fundamentally different between humans directly experiencing another world and receiving reports from an AI proxy? Does an AI probe truly explore in any meaningful sense, or does it merely collect data? These questions touch on deep issues about consciousness, experience, and the value we place on human presence versus human knowledge. Some would argue that sending AI to explore on our behalf is sufficient, that what matters is expanding human knowledge regardless of whether humans are physically present. Others might contend that there's something irreplaceable about direct human experience of new environments, that exploration requires consciousness and subjectivity in a way that even the most sophisticated AI cannot provide. These philosophical positions lead to different conclusions about whether AI-based exploration is an acceptable compromise or a fundamentally impoverished substitute for human presence. The comparison between interstellar travel and other seemingly impossible challenges that humanity has overcome might seem to offer hope, but these analogies break down upon closer examination. We often hear that human flight was once considered impossible, or that splitting the atom was thought to be fantasy, or that going to the moon was deemed impractical. Yet we achieved all these things. Doesn't this suggest that interstellar travel is simply the next challenge waiting to be conquered by human ingenuity and determination? The critical difference is that previous impossible challenges were fundamentally engineering problems, limited by current technology but not by known physics. The laws of aerodynamics permitted flight. We simply needed to understand them and build machines that exploited them. The atomic nucleus contained enormous energy that could, in principle, be released. We simply needed to understand the nuclear forces and develop the technology to trigger fission. The moon was distant, but within reach of sufficiently powerful rockets that obeyed known physics. Interstellar travel, at the scale and speed that would make it practical, runs into what appear to be fundamental physical limits rather than merely engineering challenges. The speed of light is not just a current technological limit, but a fundamental speed limit of the universe itself, according to our best understanding of physics. The energy requirements for relativistic travel aren't just beyond our current capabilities. They may be beyond what's practical for any civilization, regardless of advancement, as they require harnessing energy sources on stellar scales. This distinction between engineering challenges and physical limits is crucial, and failing to recognize it leads to false optimism about interstellar travel's feasibility. That said, our understanding of physics is certainly incomplete, and there remain deep mysteries about the nature of reality that physics has not yet resolved. Dark matter and dark energy, which together apparently constitute 95% of the universe's mass-energy content, remain poorly understood despite decades of research. Quantum mechanics and general relativity, our two most successful physical theories, appear to be incompatible in their fundamental formulations, suggesting that a deeper theory of quantum gravity might reveal new phenomena or possibilities. Speculative ideas like the holographic principle, theories of extra dimensions, or quantum entanglement effects might point toward physics we don't yet understand that could potentially enable new approaches to interstellar travel. However, betting our hopes on undiscovered physics is an uncertain proposition, and we must plan based on what we actually know rather than what we hope might be discovered. The impact of eventually accepting interstellar travel's practical impossibility on human culture and self-conception would be profound and difficult to predict. Much of our science fiction imagines a future where humanity spreads across the galaxy, and this vision has inspired generations of scientists, engineers, and dreamers. If we come to accept that this future is not achievable, that we are likely confined to our solar system for all foreseeable future, how does this change our collective dreams and aspirations? Does it make our cosmic perspective smaller and more limited? Or does it refocus our attention on making the most of our solar system home and preserving the precious biological heritage of Earth? Different people would respond differently to this reality, but it would certainly require a recalibration of expectations and hopes. Some might find this limitation depressing or claustrophobic, seeing it as evidence that the universe is hostile to life and that humanity's future is more constrained than we hoped. Others might find it liberating, removing the pressure to constantly expand and allowing us to focus on creating sustainable, flourishing civilizations within our solar system. The recognition that Earth and its biosphere might be unique, or at least that we'll never encounter other instances of life directly, could potentially increase our appreciation for the fragility and value of what we have here. If we cannot escape to other worlds when we damage this one, then environmental stewardship becomes not just morally important, but existentially critical for our species' survival. The legacy we leave for future generations with regard to interstellar travel depends largely on how we frame the challenge and what we invest in today. If we pursue speculative crash programs aimed at achieving interstellar flight with current or near-term technology, we risk wasting enormous resources on efforts that will likely fail, potentially discrediting space exploration more broadly and leaving future generations with nothing but expensive failures. If instead we invest in fundamental research in physics and propulsion, in developing robust closed-loop life support systems, in establishing sustainable human presence throughout our solar system, and in building the scientific and engineering knowledge base that might someday enable our distant descendants to attempt interstellar journeys if they choose, then we leave them with capabilities and options, even if we don't solve the interstellar travel problem ourselves. The latter approach requires patience and humility, accepting that we're laying groundwork for projects that might not come to fruition for centuries, but it represents a more realistic and ultimately more valuable investment in humanity's future. In conclusion, the impossibility of reaching Proxima b with any technology we can currently envision is not the result of any single factor, but rather the convergence of multiple fundamental challenges, each individually daunting and collectively overwhelming. The immense distances involved, measured in years even at light speed, create a time and space barrier unlike anything humanity has previously encountered. The energy requirements for accelerating any significant mass to relativistic velocities exceed what we can practically generate or store by orders of magnitude. The hazards of interstellar space, from high-energy particles to dust grains that become relativistic projectiles, threaten any spacecraft traveling at the speeds necessary to make the journey in reasonable time. The limitations of human biology and psychology make multi-generational voyages extraordinarily challenging, even if we solve the technical problems of propulsion and protection. The economics of sustaining commitment to a project spanning decades or centuries of development and execution strain our institutional capabilities, perhaps beyond breaking. And underlying everything, the fundamental laws of physics as we understand them impose limits that may prove absolute regardless of technological advancement. This reality doesn't mean we should abandon dreams of understanding worlds beyond our own or give up on space exploration. Rather, it suggests we should focus our efforts where they can be most effective, studying distant worlds through increasingly sophisticated remote observation, while expanding carefully and sustainably through our solar system, developing the technologies and experience of living in space environments that might eventually enable our distant descendants to attempt what remains impossible for us. The universe is vast, ancient, and largely empty, and the gaps between stars may remain permanently unbridged. Accepting this limitation with clear-eyed realism doesn't diminish human achievement or potential, but rather refocuses it on what is actually achievable, on making the most of the extraordinary opportunity we have to understand and preserve the phenomenon of life and consciousness on this pale blue dot that is our home. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.